taking 100 pounds and we're multiplying it by 0.5 feet. Familiar with the concept of torque? That's what torque is. Torque is a measure of our rotational energy. Okay? How much we can crank something up. Okay? Most classically, how we get a flywheel going in a car, right? Where moments are going to come into play for us is we're classically going to look at beams. Okay, we're going to look at simple beams. We're going to pin them on one side. We're going to put them on a roller on the other. And what we want to make sure is that when we set up our beam and we put all sorts of goofy types of different loading to this thing, that our beam doesn't just go spinning out. Okay? And we can think about beams. I mean, if we oversimplify, this floor could be reduced to a beam if we thought about it in 2 dimensions, right? And we were little stick figures instead of 3-dimensional humans. You can think about the bridge out there as a simple beam, right? In fact, you can take a look at them. They are simply supported. If you look at the section right out here, so they've got a pin support on the west side. Over on the east side, they're on a roller support. So that allows the beam or the bridge deck to shrink and expand. It's shrinking now in winter. Concrete's pulling back on itself, right? Then the summer, when it heats up to 80, 90 degrees during the summer days, that concrete can expand back up. Okay? It's not to the point where we can visually see it, but there is a little bit of give on that thing. That's why oftentimes we use roller supports. Okay? So we will do some homework problems where we will determine if we are at equilibrium. And so let's consider a beam. Put a roller here. Put a pin here. And we'll apply some forces. Sorry. No, that's okay. So now we're considering, over here we only considered that we needed all our forces to equal 0, right? So that we didn't tear this thing out of the ground. But now we want to not make sure that not only do we not tear this thing out of the ground, we don't cause this thing to go spinning out into the void. Okay, so we need to make equal 3 conditions. We need to make sure the sum of all our x forces equals 0. The sum of all our y forces equals 0. And the sum of all our moments equals 0. And if you don't know this Greek letter sigma, it's notation for sum. Okay, so if you think to Excel notation, when you want to take a group of cells, put in the sum function, it's the same thing. Okay? So, as we look at this beam, we're set up real nicely in the x direction, right? Because we don't have any sort of depth to our beam, do we have any forces operating in the x direction? Nothing's operating, right? Nothing's trying to push on this bridge. Okay? So we're good there. What about in the y direction? Do we have some forces? We have 2 forces, right? Now, what must our beam do so that when we put this 200-pound and this 100-pound force on it, this beam doesn't just get pushed down through the floor onto the classroom beneath us? They get a bunch of dry erase markers settling on their head in the classroom below us. wondering what we're doing up here. What do we need to do? We've got to provide resistance, right? That's why we put our reactions here. So we will call this one R2. We will call this one R1. Okay? Okay, so we need to satisfy this equation. Does anybody know how to solve a system of two variables with one equation? Did you learn that in algebra? Or they don't teach that anymore? That's a trick question, right? We can't solve this one. Okay? So we need another equation. How are we going to figure that out using what we now know about moments? What could we do?
Do the moments at R1 and at R2 separately.
Okay. Which one do you want to do first?
R2, because then it makes the 100 times 0.
Okay. Oh, I see what you're saying. So we're going to look at moment about R2. Okay? And so the moments about R2 have to equal 0. So we have how many forces are going to create a moment about R2? Aaron already told us, but is this one going to create a moment? How far away is it from R2? 12 feet, right? So it's got a magnitude, it's got a distance, so it's going to try and rotate. Okay? So here we should talk about how do we assign a positive or a negative value. And how I was taught is you take your frame of reference and you wrap your hand around it with your thumb pointing out. And if the force exerts a moment as the way your fingers curl, it's a positive moment. Okay? So that's left-handed. Now, if you're right-handed, or if you're left-handed, sorry, if you left-handed, maybe you'd like to do this. The reason that I use my left hand is now I can write while I reference what's going on with the moments, right? If you write left-handed, maybe you want to reference this way. Okay? It doesn't matter as long as you apply it consistently. Okay? So from my perspective, I've got my left hand down, my thumb is pointing out towards me. Anything that creates moments with this type of rotation is going to be positive. What's this 200-pound force going to do? With reference to R2. It's going to try and crank this way, right? So it's going to be negative. So we have minus 200 pounds. How far away is it from R2? 12 foot, right? Okay. What about R1? What's R1 going to do? It's going to try and crank this way, right? How far away is it? 8 foot, right? What's 100 pounds doing? Is it rotating? How far away from R2 is it? It's right on top of it, right? So it's not going to create any sort of rotation. It's just pushing right down onto the thing. Okay? Same thing for our reaction at R2. Okay, so these aren't going to contribute. So now we've got an equation with one variable, and we have another equation with two variables. So we can solve our R1 down here, plug our R1 up here to solve for R2. So, Aaron, you don't have to solve about both points. Okay? But it could be something that you do. Okay, so 0 has to equal minus 2,400 pound-foot plus 8 R1 pound-foot. Everyone see what happened there? So here I added 2,400 to each side. Sorry, 2,400 pound-foot to both sides. Then divided out 8 feet. Okay? Comes down to 300 pounds. What's that going to mean for R2?
0.
R2 is nothing. Structural redundancy. Okay? So it does not need to require, it does not need to carry any sort of that resistance. It's just there hanging out. Okay? Questions? Comments? Concerns? I have to take a picture of it. There's going to be a video online later.
Oh, it's true.
It's hard to break habits, right?
Yeah.
Okay, let's take a look at one more and then we'll call it a day. Oh. So over here, we dealt with real nice point loads. Okay? You're also going to see uniformly distributed loads. And all that means is that we've got something on here that weighs 100 pounds per foot. Okay? Maybe there's some sort of bracket that's welded on to the thing. We don't know what it is. Okay? We also have a 400-pound point load. And that's located 4 foot from R1. Our uniformly distributed load starts 6 foot from R2 and ends over our roller support. Okay? So, we'll set up our equilibrium conditions. Make sure this thing doesn't go spinning out on us or push down into the earth or slide right off the board, right? Are we worried about it sliding off the board? We're not applying anything in the X direction, right? So we're good there. What do we need to do to make sure this thing doesn't get pushed down through the board? What do we have to satisfy? What are we going to do with this thing?
Yeah, it'd be times 6 because it's 6 feet per foot.
Good? So R1 plus R2 minus 400 pounds minus 600 pounds all has to sum to 0. Okay? Good? How do we want to look at rotation? Pick a number, 1 or 2, right? Flip a coin. Doesn't matter. Look about 1. So our moments about R1 have to equal 0. So what's 400 pounds going to do? It's going to try and spin this way, right? How far away is it? 4 foot? Okay. Uh-oh. What about this thing? Good. Yep. We'd resolve. So we want to resolve it into a point load. Okay, so when we talk about rotation, a uniformly distributed load will cause the same amount of rotation as a point load, 400, is that high? Applied at its midpoint. Okay? Does that make sense to everybody?
Yeah.
So we're going to drop 600 pounds 3 feet from R2. So how far away from R1 are we? 9 feet. And how are we trying to rotate that thing? Trying to spin it this way, right? £600 times 9 foot. What's R2 doing? Spinning this way, spinning this way, spinning this way, right? How far away? 12 feet, right? Okay? So, 1,600 pound-feet plus 5,400 pound-feet minus 12 R2 pound-feet. Oh, that's going to give us kind of funky number, huh? So 7,000 pound-foot divided by 12 feet. 58 something? 57 something? What?
7,000 divided by 12.
Oh yeah, sorry. Should have been 120. 583?
Yep, 0.33.
Yeah, 583 is close enough for us. Okay, so R2 is 583, so how much is R1? What's that?
Plug it in.
Yeah. R1 plus R2 has to equal 1,000, right? So if we're 583, R2's got to be 417, right? That's all there is to it. Good? Okay. We'll let it rip. The homework's posted for you. This assignment is a little bit longer than we typically will do. So we'll check in and see how you're doing on Thursday and see if we need to adjust the due date based on our progress. Okay? So if you got questions, come with those. We'll lead off on Thursday. Then we'll talk about force polygons and what we'll do in lab next Tuesday. Okay? Thank you.